So, welcome to online classes. Now we are going to discuss about vector magnetic potential, which is represented with a bar. So, what is vector magnetic potential? So, the curl of vector magnetic potential gives the magnetic flux density B bar. Flux density B bar, where that is curl of vector magnetic potential A bar is equal to B bar. If you can observe here, curl of vector magnetic potential means where A bar is called vector magnetic potential and whose units are Weber per meter. Because of this is curl of A bar, this is B bar. So now if you can go to curl means it is, for example, dou by dou x that is equal to B bar. So dou by dou x means 1 by meter, B bar means Weber per meter square. Then A bar is equal to Weber per meter square into meter. Here meter and meter cancel, then Weber per meter. That's why the units are Weber per meter for vector magnetic potential A bar. To tell you how to define the vector magnetic potential means the curl of vector magnetic potential gives the magnetic flux density B bar. That is curl of A bar is equal to B bar, where A bar is called vector magnetic potential. This is the basic definition of vector magnetic potential. Now we will go for properties of vector magnetic potential. Properties of vector magnetic potential. Properties of vector magnetic potential. So the first property is the vector magnetic potential is defined when the regions are having current to density also. So that's why it is different from scalar magnetic potential. Because of scalar magnetic potential is applicable for only the regions which are having zero current density. But vector magnetic potential is applicable even the regions which are having current densities. So how to prove this statement? The first property. How to prove the first property? So from the relation between B bar and H bar, that is equal to B bar is equal to mu naught into H bar for a free space, mu r is equal to 1. So then here H bar is equal to mu naught by H bar is equal to B bar by mu naught. H bar is equal to B bar by mu naught. By taking curl on both sides, curl of h bar is equal to curl of b bar by mu naught. Since mu naught is a constant, then curl of h bar is equal to 1 by mu naught curl of b bar. We know that b bar is equal to curl of a bar. Then curl of h bar is equal to 1 by mu naught curl of a bar. So here which is equation number 3, but curl of h bar is equal to j bar, then j bar is equal to 1 by mu naught curl of a bar. So from vector identity rules or from vector calculus, plus curl of a bar is equal to del of a bar minus del of a bar is del square a bar. So from vector calculus, curl of a bar is equal to del of a bar minus del square a bar. So if we can substitute this continuation equation, that is continuation equation number 5. So substituting equation 5 in equation 4, we get j bar is equal to 1 by mu naught into del of dot a bar minus del square a bar. So but where del of a bar, that is del square a bar, is equal to 0. From the vector identity rules, del of a bar is equal to 0, then j bar is equal to 1 by mu naught minus del square a. Then j bar into mu naught is equal to minus del square a bar. So then del square a bar is equal to j bar into mu naught. Del square a bar is equal to j bar into mu naught. It is minus del square a is equal to minus j bar into mu naught. So which is equation number 6. So if we can observe that in electrostatics, del square v is equal to minus rho v by epsilon naught. So which is called Poisson's equation in electrostatics. Now here also del square a bar is equal to minus j bar into mu naught is called Poisson's equation in magnetostatics or magnetic fields. And also if you can see here, this vector magnetic potential is defined for j bar. That means in that field is defined at j bar. That field is defined at current density. That field is having current density j bar. That's why the statement is proved. The first property statement is proved. So here where equation 7 is called Poisson's equation in magnetostatics. So then next property, second property is vector magnetic potential A bar can obeys both Laplace's and Poisson's equations. From equation 6 and equation 7. So third property is vector magnetic potential due to simple configurations. Due to simple configuration. In next class, we will discuss this. In next class, we will discuss this.